In this video, we'll continue our review of hypothesis testing, moving on to reviewing how we actually construct some of the hypothesis tests. So in hypothesis testing, depending on what textbook or protocol you're using, we have different steps that are involved. These first ones, and I should say that the different steps that are involved, they're not really different steps. We just combine some. So for instance, step 3, collect sample data and compute the test statistic. Maybe 2 different steps in a different protocol to lead to a 6-step approach instead of a 5-step approach. The main ideas are writing the null and alternative hypothesis, specifying our level of significance, and if you have no idea, 0.05 is a good default. Actually running your study and collecting data, computing the value of the test statistic, and then we go in 2 different directions. In the last video, we very quickly covered the p-value and the critical value approach, mentioning that the p-value approach, if p is less than alpha, then we reject the null. If p is greater than alpha, then we fail to reject the null. And again, these terms, reject the null and fail to reject the null, are technically specific and are terms I will expect you to use in this course. Typically, this says use the value of the test statistic to compute the p-value, and that's actually exactly what happens. But typically, when we do a p-value approach, we don't do this. We use software that is part of the analysis, spits out the p-value. The p-value approach is kind of annoying to do by hand, frankly. But in software, because programmers build out the nice software to give us this without us having to do any more work, the p-value approach is really, really useful, and in fact, a lot of researchers tend to prefer it. The critical value approach is what we tend to do if we're doing this by hand. That is, we find a level of significance. So for a z example, we might find, well, what's the cutoff for a one-tailed z-test so that alpha is on one side of the distribution, the low tail or the high tail. Or if it's a 2-tail test, we split alpha in half and figure out, okay, what z-score gives us half of the alpha above and half of the alpha below. And then we kind of plot visually, or you can even draw this out, plot the test statistic onto that curve and see, does the test statistic fall into these regions of significance? And again, if it's a high tail test, the region of significance is on the high side of the cutoff. If it's a low tail test, the region of significance is on the low side of the cutoff. And if it's if it's a 2-tailed test, the region of significance is on the outside of the tails. And again, these are nice things to write down if you want these little rules of thumb to go back to and remember. Just pause, rewind, and jot it down. And then try it out on a couple of the examples we're going to talk about. Now, computing the value of the test statistic, one of the questions is, well, what is the value of the test statistic? The answer, honestly, is it depends. I have here the value of the test statistic when the population standard deviation is known. And as we talked about with the confidence interval, that relates to z. Now this gets confusing because this is a z-score, but this is the z-score test statistic. So sometimes I'll write a little TS underneath it, or a little crit underneath the z for the critical value if we're doing critical value approach. But do be aware that oftentimes this is how it's written. And I do apologize because it is written ambiguously, and that can be kind of frustrating. So kind of keep your eye out and look at the context. Are we talking about a test statistic, in which case z would probably represent the test statistic? Or are we talking about some kind of a critical value? Now, this is the test statistic just for this particular case. So if I was doing a case where the standard deviation was not known, then this test statistic notation z would actually be changed to a t, because when I use s instead of sigma, the sample standard deviation instead of the population standard deviation, excuse me, then that takes me to a t distribution. So what you're seeing is that the notation for the test statistic tends to connect directly to the distribution we're going to end up comparing it to. So if you're feeling good about this, go on and pause the video and give this problem a shot. So give it a shot right now if you want to. All right, so I'm going to keep harping on this because it is really important. The thing is that which equation do we use for z? Remember, we had x minus mu over sigma, and then this x bar minus mu over sigma divided by the square root of n. And we talked about this in the last lecture, how that relates to the or 2 lectures ago, I suppose, how that relates to, are we looking at a sample mean or are we looking at individual values? So in this case, we're looking at response times for a random sample of 40 emergencies, and we're looking at a sample mean. So we're going to be using that x bar minus mu over sigma divided by the square root of n equation. If this had said we're looking at individuals, then that would be different. But here we have the sample mean, and we took a random sample, and that appears to be what we're studying. Now, the population standard deviation, this is of individual response times. This is not of the sampling distribution. So this is important to know. This is going to be our regular sigma, and we can use that to calculate sigma sub x bar. I want to perform a hypothesis test to determine whether the service goal of 12 minutes or less was being achieved. So we actually talked about this example before, where we developed the hypotheses. We had the null hypothesis is that it's less than or equal to 12 minutes, and then we're looking for any evidence if something is wrong in this case. Is anything bigger than 12 minutes? And again, the reason that the less than or equal to, it is what they're interested in, but it's or equal to, and we said that equal to's fall within the null hypothesis. That's why that's there. Level of significance can really be anything, but again, unless you have a very good reason, we tend to set it at 0.05. That's the industry standard, if you will. And then we compute the value of the test statistic by literally plugging in the values from the previous slide into this. Sometimes it's nice for me when I'm reading a problem to write down each of the elements that I need. So I need to know what x bar is, mu 0, sigma, and n in this case right here. So maybe quickly, and I know these videos take a while, they're supposed to be review and go a lot quicker, but I also know that some students like kind of working this out together. It has been potentially a while since you've seen this, so I suppose we can go a little slower. That's fine. So x bar mu, that should be mu sub 0. This is the null hypothesized value of mu. That's why it has a little sub 0, as it's what's talked about in the null hypothesis. And then sigma and n. So what is our sample size? And I do the easy ones first. So sample size, well, I've got a random sample of 40. So 40 is going to go n equals 40. Sigma, what's my population standard deviation? Well, it literally says the population standard deviation is 3.2. Now, how this actually works is if it says population standard deviation, I know I'm using the z equation, so I know I'm going to be using sigma. If it says sample standard deviation or just gives me a data set and I have to calculate the standard deviation from the sample, then I know I'm using the t, so I'm going to have s here instead of sigma. So this helps me not only know what the value is that I need to plug in for the eventual equation, it helps me to pick the right equation in the first place. Again, population standard deviation connects with z, sample standard deviation, whether it's given in the problem or whether you calculate it by hand from a data set, that connects with t. X bar, the sample mean, and again, it's good to know what this notation means. Sometimes I say statistics is like learning another language. In some ways it is. If I don't know that x bar means the sample mean, I could like read through all of this and any of the numbers could be x bar. But if I know x bar literally means the sample mean, Okay, so read the problem and see the sample mean is 13.25. Oh, okay, so 13.25 next to the sample mean. All right, so what is the null hypothesized value, the nothing's going on value that we mentioned in our null hypothesis? Well, if I can go back to the null hypothesis and write that out, actually, sometimes that's the easiest way. I connect back to my null hypothesis. It's based around this number 12, so I plug in 12 for this mu 0. Another way is to look at the client or the person I'm working with or the person the problem's about and to see what do they care about. So they're caring about this number 12. That's kind of where their focus is. So that often is going to be what my mu 0 is, that default value, because that is their frame of reference that they're telling me. So the sample mean, the population standard deviation, all of this comes from data. But this person, the EMS director, they made this number 12 up. It's got some theoretical or clinical significance to them. So this is our reference mu 0. After I have all these pieces, I literally just plug them in and type them into the calculator. In my previous stats class, if you've taken it with me, then you'll know I love telling students, hey, I'm going to give you points for this. You literally, like, it's like a hunt and find puzzle, and then you plug in the answer into your calculator, and you get points. Isn't that amazing? So in this case, this would be the calculation of the z-score for that word problem. And again, this is the z-score for the x bar relation to its sampling distribution. All right, so let's look at this, the p-value approach. Well, so if I'm doing a p-value approach, if I have a one-tailed test, then I would look at the area above the p-value. So if I've got my curve, I'd write my test statistic, TS, and then I'd look at the area that's above. This is for a one-tail. Sorry for my terrible, terrible handwriting. It's hard to write with a mouse. But for a one-tail, this is the area above that test statistic. So that's what I'm looking at for a p-value in a one-tail, upper-tail test. If it's a one-tail, lower-tail test, I'd be looking at the area below the test statistic. And if it's a two-tail test, I'd be looking at the area that is more extreme than the test statistic. If it's above the middle, then the area above. If it's below the middle, then the area below. So the area more extreme than the test statistic and multiplying that by 2. Now that's a little trick. You may want to jot that down if you ever have to calculate p-values by hand. On a two-tail, you look for the area more extreme and multiply by 2. But here we have an upper tail, so I look at the test statistic and the area above it, and that is my p-value, the probability of as or more extreme statistic under the null hypothesis to be found in a future sample. So in this case, that is 0.0068. That is clearly less than our cutoff value of 0.05, so we reject the null. What does that mean? We reject the claim that the time is less than or equal to 12. So there is sufficient statistical evidence to believe that EMS is not meeting the response goal of 12 minutes. And I like this explanation. Why do I like this explanation? Excuse me. I like this explanation because we talk about evidence. So again, we didn't prove that they're not meeting the goal. This isn't a conclusion that they are definitely not meeting the goal. We're saying that we have evidence to believe statistically that they're not meeting the goal. Now, what if we found this out and it was actually the sample mean was 12.01 minutes, but we still had enough evidence to infer that it's not meeting the goal, that they were at 12.01 minutes? Well, this separates what I call statistical and practical evidence. Sometimes you'll hear people call it that. You'll also hear it called statistical and clinical significance. So here we have a statistically significant finding. As to whether or not that finding is clinically significant, that's tougher to tell. Typically, what I would do is calculate a confidence interval. I'd look at the low end and the top end, and I would bring those to my client, this EMS director, and I'd say, hey, this is the reasonable range of values as to where you're currently falling. 12 isn't in there. This is bigger than 12 according to this hypothesis test. And confidence intervals do line up with hypothesis tests. So if the confidence interval doesn't have the value, the hypothesis test is going to say to reject the null. And then you would have that conversation and look at the top and the bottom values and say, okay, well, which one, if either of these is meaningful for you, and we would then go through a conversation about if that meaning happens. So here's a picture of what's going on. The p-value, again, we plug in the test statistic. We calculate the area to the right-hand side of it. This is the cutoff value, and you can actually see that if I was doing the cutoff method, if I created my region of rejection, then this test statistic value falls within the region of rejection for the cutoff. So this picture actually shows both the p-value and the critical value approach. Speaking of the critical value approach, let's look at this real quick. So it's an upper tail test. For alpha equals 0.05, I look in my table. I find that the cutoff on the top end, so that I only have 0.05 error on the upper end for an upper tail test. The z value for that is 1.645. And we're going to reject the null if the test statistic is bigger than 1.645. So again, we're looking at comparing the test statistic to the critical value in the critical value approach. In this case, because our test statistic is bigger than the critical value, we reject the null hypothesis. And again, this bigger than versus less than versus outside of the two edges of comes from, is it an upper tail test, a lower tail test, or a two-tail test? Upper tail test, I want it to be bigger in the upper direction. Lower tail test, I want it to be smaller in the lower direction. Two-tail test, I want it to be on the outside edges, one of the outside edges, for significance or to reject the null hypothesis. So in this case, again, we have evidence to believe that the EMS is not meeting this particular goal at the population level. And again, this is the cool part about what we do with statistics. We don't know if the population response goal is 12 minutes or less. We only looked at 40 different response rates. But we, through the use of statistics, can make an inference about all of the rest of them based on just these 40 responses. And this is the cool part about statistics, is how we can connect a limited sample to a potentially infinite population and make meaningful conclusions using probability and evidence. Again, unfortunately, because we don't know and because we are only using a small sample, we can't prove that this is the case. We can just say we have evidence that this is statistically significant. So we have already talked about this somewhat, but if we're doing two-tailed hypothesis tests for the p-value, again, we're going to look at the test statistic and we're going to go more extreme. So if it's on the right-hand side of the peak, then we're going to go out to the right and look at that area. If it's on the left side of the peak, we're going to go out to the left and look at that area. So we're going to go more extreme, and then we're going to double that value to get the p-value for a two-tailed test. For the critical value for two-tailed test, we're going to kind of do the same thing, except we're going to split the area into both sides, just like we did with the confidence interval. This should be very, very familiar. Now, the rejection, again, is we're looking for more extreme on either edge. So are you below the low cutoff? Are you above the high cutoff? That's how we're making our decision in this. If you feel comfortable, go on and pause this, give it a shot. We'll come back to it in just a second and go through it pretty quick. All right, so we're checking toothpaste, and we want to make sure it's within a reasonable range. Now, personally, I like confidence intervals for this because a confidence interval would tell me, well, based on the sample, what is the reasonable range of the population value. I think it gives a little bit more information, and I know I went on a bit of a lecture about that at the beginning of this lecture set, a bit of a soapbox about it. But in this case, again, I think it'd be more useful. We can, though, if we were just asking the question, is this bigger or less than or different, we can use the hypothesis testing method. Now, notice in this particular case, they don't care if it's less than or more than. They just want to know if it's different. So I'm going to be using the equals and not equals null and alternative hypothesis. Also note that I'm asking you about a tricky alpha level here. So you're actually going to have to go and dig through those z-tables and not use the pre-constructed values for the critical value approach. Of course, you're still going to have to do it for the p-value approach with the test statistic if you're doing that by hand. All right, so we've got a two-tailed test, equal to 6 or not equal to 6. Level of significance is 0.03. Then we're going to calculate the test statistic. We found our sample mean to be 6.1. The value that they care about is 6. Our population standard deviation is assumed to be 2, and then a sample size of 30. Get a z-value of 2.74. All right, so to compute the p-value, we would draw out our curve, find the z-score, look at the value that's more extreme. In this case, it's on the top end, so I'd look at the area above that test statistic score. And then I would take that area and multiply it by 2. So in this case, this is the area above the score. This is the area below the score. 1 minus that's the area above the score. And then I'm multiplying it by 2 to get 0.0062. Because this is less than our alpha value of 0.03, we reject the null. And then we have evidence to determine that that there is a difference, that the mean is not 6. So yeah, I don't like the alternative hypothesis is true. That doesn't mean anything if I'm telling it to anybody. This is technically statistically correct. But what we actually mean is that there's evidence to believe that the mean filling weight is not 6 ounces. In this case, we have evidence to believe that it is over 6 ounces. So again, you can see we found the p-value at the top end. The area was 0.0031, and then we multiplied that by 2 because it could have been more extreme in either direction, and we want to account for that fact. So the probability of as or more extreme statistic, well, as or more extreme in the top end would have been significant, but so would as or more extreme in the bottom end. And the reason why is because this was a two-tailed test. We didn't know which direction this was going to fall in. All right, so for the critical value approach, again, we split our alpha. We dig through our table to find, okay, well, what z-score is going to give me an area of 0.015 above and below, and again, because we're using the normal distribution, nice and symmetric around 0, this is just going to be the positive and negative version of this cut score. So looking at this, again, we've got our curve, we've got our 2 cut scores, and if it falls on the outside of either of these cut scores, that's what's going to tell us it's significant. So negative 2.17 if it falls below negative 2.17 or above 2.17. This case, 2.74 falls above 2.17, so this is when we reject the null hypothesis and say there's sufficient evidence to believe that the mean filling weight is not 6 ounces. In our case, we can look at the sample mean, 6.2 ounces, and say there's sufficient evidence to believe that the sample mean, or that the actual population mean is above 6 ounces. And this is important. Again, I mentioned this previously. We're using a sample to make claims about the population. This claim, so pause, put down your cell phone, whatever you got to do. This claim is not that the sample mean is different than 6 ounces. The sample mean 6.2. Of course it's different than 6 ounces. 6.2 doesn't equal 6, period. So we're not making claims about the sample mean. That would be really obvious. We're making claims about the population mean based upon the sample mean in our statistical distribution. So we're combining that sample mean of 6.2 and the stats distribution, and we're making claims about the whole population, about all of the average filling weight for all of the toothpastes. So in this particular case, that's really, really important that when we say there's sufficient evidence to believe that the average filling weight is not 6 ounces, we're not saying there's sufficient evidence to believe that the average filling weight isn't 6 ounces in the sample. We're 100% sure of that. We're saying there's sufficient evidence to believe that the average filling weight is not 6 ounces in the whole population. So again, this is why the statistical process is cool, is we take a limited finite sample, sometimes a pretty small sample, and we can make really grandiose claims that's supported by mathematics and logic. So again, we create our cutoffs. This is just a prettier picture, a much, much, much prettier and more legible picture of what I just drew on the last slide. Then we've got our rejection regions on the outside and the fail to reject region on the inside. So I believe I mentioned this earlier, but we can actually use confidence intervals to do hypothesis tests. Now, confidence intervals, because we use the z alpha over 2 critical value, can only be done on two-tailed hypothesis tests, not one-tailed hypothesis tests. But pretty much what we do is we have our interval, and if the mu sub 0 is within the interval that we create for the parameter estimate, if mu sub 0 is in the interval, then we fail to reject the null hypothesis. If mu sub 0 is not in the interval, then we reject the null hypothesis. Honestly, mathematically, if we're using continuous values, this should never be true. This idea of mu sub 0 is equal to one of the endpoints. So honestly, if mu sub 0 is equal to one of the endpoints, I would not reject the null. That's not particularly strong evidence. At the very least, that's borderline. At the worst, that's really not convincing. So I'll disagree with our book here that I would not do this. I will say that in, 10 years of practicing, I've seen this happen one time. And it was really cool. I was working in a stats consulting lab with a whole bunch of master's and PhD statisticians. And I was working with a client, and this happened. And I called everybody, and everybody in the lab kind of went and huddled around the computer and said, "Oh." So this is extraordinarily rare to happen. I really shouldn't be making this big of a point about it, but if this happens, I mean, the whole point is to convince yourself that you have a convincing argument that the null hypothesis is not true. So if it's on the borderline, you have to ask yourself, is this really convincing or not? And that can be kind of a personal decision. Mathematically, though, this should never happen. So actually, in the theory, this case is not particularly discussed because in the theory, two continuous numbers, the probability of two continuous numbers equaling each other is 0. Anyway, more information than you wanted to know. Just think about if mu 0 is in the interval, fail to reject. That is, we don't have enough evidence to reject the null hypothesis. We don't have enough evidence to think something interesting is going on. If mu sub 0 is not in the interval, then we can reject that mu sub 0 hypothesis. And we do have enough evidence to believe that something interesting is going on. What's cool about the confidence interval approach is that actually we can test multiple mu sub 0s very quickly. We can say, okay, well, what are these reasonable values for these mu sub 0s? And again, you'll hear me call the confidence interval a range of reasonable values. And it really is how I like to think about it and explain it to others. Because practically that's what it is. Our point estimate, that best guess, that x bar or p hat or sigma hat, those are our best guess if I had to provide a single number. But I know that single number is wrong, so I give myself a little bit of wiggle room. And within that wiggle room, those are a range of my best guesses as to where the true value falls. Again, we don't have to use nice numbers for the confidence intervals. If I asked you to calculate a 97% confidence interval, you're just going to use z sub alpha over 2. So z sub 0.015, 0.015 being half of 3%, gives you 2.17, and then you would put together this interval, and then I could test this idea of 6 versus this value. Note that this gets really, really close to 6, and this is actually an argument for why people prefer to use the confidence interval approach even if they're doing hypothesis tests. The reason is because the confidence interval approach doesn't just tell you reject or fail to reject. It tells you, well, what is the reasonable range? And then you can bring this back to the floor manager of the company and say, well, it technically 6 isn't in this limit, but 6.02 is the lower end of a reasonable value. Perhaps that's good enough. And if this individual says, well, we need some more details, then you could run another study and find some more details. If this individual says, well, no, that makes sense to me and this is good enough for us, then you may determine based on this confidence interval that while you technically would reject the null hypothesis according to the hypothesis test, so it is a statistically significant difference. Practically, the difference of 0.02 ounces is not meaningful enough to make large changes. So that looking at this interval, you'd say, yeah, without more information, we're not going to make a change. All right, well, we'll go on and cut this video here. In the next and final video, this lecture set, we will be discussing the other situations. Those will go quite a bit quicker because we've already covered all the groundwork. So we'll be talking about T and the population proportion and moving on from there. And then after that, we will have our first R day. So again, please make sure you've got an R in R Studio downloaded and all set up. And then we'll be having our first video where we are jumping into that.